The topic of the talk is introducing Cassini the Slingshot Interconnect. Here's the floor is yours.
Gotcha. All right, so we've talked a lot about Slingshot in the past in various forums. We haven't said as much about the NIC that's associated with it, which we call Cassini. And so I'll talk through a little bit about that today. Right. Okay. Obligatory marketing slide first. This just sets up what we were trying to achieve with Slingshot. So on the left here, there's the attributes of a traditional Ethernet network. There's good things about it. It's everywhere. You can plug anything into it. There's a big ecosystem for it. It runs IP everywhere. But there's some bad things about it. It's not terribly efficient for small packets. It tends to be higher latency. It tends not to scale well. It tends not to implement HPC-oriented features. On the right-hand side, there's a kind of list of characteristics of HPC interconnects, traditional HPC interconnects. And there's some bad things about them. They're traditionally single vendor solutions. They have limited connectivity. A lot of traditional HPC systems have gateway nodes to bridge from the HPC interconnect out into the broader data center. Those aren't typically very fast, and they tend to add cost and power to the system. But there's important good things about them. They're low latency networks. The HPC interconnects are efficient for small messages as well as large. They support things like tag matching and atomic operations, and they scale out to large HPC systems. And so what we did with Slingshot was to bring the best characteristics of those two networks together into one converged solution. All right, sorry, it's a marketing slide, so it's got to build. So some of our objectives with Slingshot, we wanted to build something that would scale out to a really large scale. So we've got a 64 port by 200 gigabit per second switch. We wanted it to be Ethernet compliant because that gives us the broadest connectivity into the data center. And so with Slingshot network at the edge of it, you can plug straight into your data center. There's no need for gateways. There's no need for special translations. It just speaks IP out into the data center. Along with our heritage, we bring forward world-class experience with adaptive routing and quality of service, 8 generations of experience building those technologies and 8 generations of learnings, bringing that into the Slingshot interconnect. One of the things we learned in those prior generations of networks is that congestion control is really important, even in HPC systems, where a lot of people tend to think of those systems as kind of single use at a time systems. They're really not. There's usually some large jobs running on a system at a time, and they can interfere with each other. And so an important thing we did in Slingshot was to implement an efficient congestion control solution. And then we put a lot of focus on uniform latency across the system, low uniform latency, because tail latency is important because real applications synchronize across the system. And so if you've got one message that takes 10 times as long as all the others, your synchronization runs at the speed of that slowest message. So we look at the components of Slingshot, and I promise I'm getting to Cassini. I just wanted to set up the context for people who might not be familiar with Slingshot. So if we take a look at the components of Slingshot, there's the Rosetta switch pictured on the right here, supports multiple QoS levels, adaptive routing, congestion control that we talked about, as well as high performance multicast and reductions. What we called Slingshot 10 was a combination of Mellanox NICs with Rosetta switches. And you saw that solution in the Perlmutter system at NERSC. That's now being upgraded to Slingshot 11 with all the other systems that we're doing. Slingshot 11 is a combination of our Cassini NIC, which provides MPI hardware, tag matching, progression in hardware, one-sided operations, and doubles the injection bandwidth of the network. So we're so close to this past June that I still have to include the obligatory picture of Frontier. Frontier, for those of you who are not familiar with it, is the first exascale system on the top 500 list. It's an HPE system that has the Slingshot interconnect in it. So let's take a look at what makes up that network. So Frontier has 9,400 compute nodes, and each of those compute nodes has 4 NICs in it. So that gives us 800 gigabits per second per direction per node. That means there's over 37,000 NICs, which comes out into 18,000 L0 cables, almost 10,000 L1 cables. You can read through the list of parts there. It's an enormous bag of parts to build out that network. An interesting note on the left, there's 2,300 management agents, 1 per switch, that have their own management network behind them. And so it's quite a large undertaking to deploy and shake out a network at that scale, especially when it's effectively serial number 1. So with that, let's start talking about Cassini. That's not a marketing for that coat there. That's it's allergy season in Tennessee from spring until fall. So, all right, Cassini is a dual NIC die. There's pictured on the right here. There are 2 completely separate NIC cores in there, each one with a 200 gigabit per second link to the network, and each one with a PCI Express Gen 4 x 16 host interface. That host interface is capable of extended speed mode. Extended speed mode is a capability that can allow signaling up to 25 gigabits per second with the Gen 4 standard. So the numbers that everybody likes to see, this is a TSMC 16 nanometer process. It's 132 square millimeters total. That's for both die on a 32 by 32 package, operating at about 30 watts when you're running at full bandwidth. And again, that's for both NICs. Now, the reason we built 2 NICs in a die in this case is really a system packaging optimization. So if you look at the node architecture for some of the early systems here, on the top center here, there's a Frontier node. You can see it's got 1 CPU and 4 NICs and 4 GPUs. Each NIC is connected directly to a GPU, so that provides for an interesting node topology for that one. On the bottom right, there's an Aurora node. That's the system that's going in at Argon. It's got 6 GPUs and 2 CPUs and 8 NICs on it. And the bottom left is a Perlmutter node in its upgraded configuration to Slingshot 11, where it has a CPU and 4 GPUs and 4 NICs. So if you'll notice, every one of these nodes in these high-end systems has between 100 and 200 gigabytes per second of bandwidth coming out of it. And so just from a system level packaging perspective, it's more space efficient for us to pack 2 NICs into 1 die. And so that's why you see that 2 NIC architecture. That said, Cassini comes in 2 forms. There's the form that's in our integrated systems. It's a mezzanine card here on the left. It's custom form factor. And then there's the industry standard form factor on the right. Now, obviously in that picture, you don't see 2 PCIe Gen 4 connectors on that card. It takes rather specialty things to do that. That's just a picture of a single interface using a single die on that right-hand side. Sorry, a single NIC within the die on that right-hand side. Let's dive a little bit more into the details. So we'll start with the network API. So Cassini exports the libfabric API. It's a multi-vendor network API. The network API sits kind of between the network hardware and the API that the user normally sees. So MPI is implemented over top of libfabric. OpenSHMEM is implemented over top of libfabric. The CRASHMEM, all of our programming environments are implemented over top of libfabric. Now, traditionally in a high-end HPC system, this network API had a tendency to change roughly every generation as it was kind of a bespoke thing for a piece of network hardware. Now that we've got a standard that has a broad set of HPC features in it, this is going to be a much more stable kind of middleware target. libfabric was introduced for that. It was originally based on Portals 4. It was and influenced by PSM. So this was created as part of the OmniPath program originally at Intel. While I was there working on OmniPath 2, we created libfabric as a way to expose those capabilities and kind of introduced that into the community, and now there are shipping versions of it from HPE as well as Amazon and Cornelis and a couple of others. One of the nice things about libfabric is that it exposes kind of natively key semantics for things like MPI and PGAS, as well as file systems. So you'll see one-sided put and get operations, two-sided send and receive operations with matching embedded into the API. You've got atomic operations and triggered operations. And it incorporates locally managed offsets, which before this, that was most prominently seen in portals. And those locally managed offsets are kind of a useful tool for building up shared queues. As we start down into the Cassini hardware, it's built to support the capabilities that are provided through libfabric. It's got specific optimizations for MPI, for PGAS, and for Ethernet. So on the MPI side, we do hardware tag matching for MPI. We do full offload with strong progression for eager messages for rendezvous transfers. Yes, we will issue the target side of the rendezvous operation back to the initiator in hardware. We do strong progress with overlap for both expected and unexpected messages. So this is not just an expected message capability, it works for unexpected messages as well, which is important because there's a lot of applications that have more unexpected messages than you would think. And so, so we offload those as well. We have a scalable ordering mechanism. So MPI has a fairly strict definition of ordering rules for matching, but we only use that ordering mechanism where necessary. So we use it to preserve the match ordering and not for the payload transport, because the less ordering we have, the easier it is to do adaptive routing through the system and get more efficient utilization of the network. For PGAS, we have a very low overhead transport protocol. We have specific synchronization and ordering accelerations that we'll talk about in a couple slides. We have an integrated atomic engine and a large address translation cache that we'll talk about as well. And then for Ethernet, so on the earlier slide, I pointed out how we were bringing the best of HPC networks and Ethernet into one network. Well, that means that the NIC has to be a good Ethernet NIC as well. That's not saying that it's going to be the best in the world at all the Ethernet transports, but it had to be a good Ethernet NIC, or being able to plug into the data center network didn't do us any good. And so we include stacks for IPv4 as well as IPv6. We have hardware checksum offloads for IP and for Rocky. We include flow steering that's either based on a hash of the 5-tuple or on a Q pair, hash of the Q pair. We have multiple QoS levels through the NIC, and we integrate with the newer Linux driver infrastructure, so the oneAPI infrastructure, the GSO segmentation offload, the generic receive offloads, all of those kind of new features of the Linux kernel for an Ethernet NIC are things that we integrate with. So as part of implementing the NIC, we built a new transport. Our goals for that, we wanted to be scalable. We couldn't have a transport state that scaled with the number of nodes or the number of processes in an application. We wanted to do better from a scalability perspective because we didn't want a memory footprint either on the node or on the NIC that scaled linearly with processes or quadratically with processes, as the case for a lot of historical networks. We wanted to be efficient, and we wanted to be efficient both for high bandwidth transfers as well as for fine-grained PGAS accesses. In the past, there have been networks from Craig that were really efficient for PGAS, but not so much bulk data. And then there have been networks from others that were more efficient at bulk data and not so much PGAS. And we wanted to achieve both, and so we've done that with the transport design for Cassini. And we wanted to build the semantics kind of natively. So we wanted to support matching in the transport. We wanted to support all of PGAS operations that are needed, low latency and fine-grained, direct memory accesses for that, as well as atomic operations. And so what do we do for that? Well, we didn't create any persistent connection state. So applications don't create connections. Processes don't create connections. NICs don't have connections per se that persist. So there's not a job starts and create connections to all the peer NICs kind of step. There's only kind of ephemeral ordering state that's created as a NIC needs it that runs NIC to NIC. So any two processes can share that ordering state. And then it goes away when there's no longer traffic flowing between those NICs. We only use that where it's needed. So we'll do sequence numbering of packets as needed to preserve match ordering, for example. But most of our payload packets are unordered. If you do a bulk transfer, most of the payload packets are unordered. And if you do a PGAS transfer, most of the packets, actually, typically all of the packets are unordered. And that helps our adaptive routing achieve a higher efficiency. We did a lot of header optimizations, and I'll have pictures about that on the next slide, where we removed some Ethernet overheads, and we did some PGAS-specific things to get lower header overhead. The transport itself was inspired by Portals 4. That gave us a lot of the mechanisms we needed to build an efficient web fabric provider. This meant that matching information was a first-class citizen in the transport. So messages get match bits on them. Those match bits flow with the message, and that's used to choose the buffer at the target. We also carry the source rank in a separate field that can be used as part of the matching information and can be delivered to the target to implement some of the MPI required semantics for populating a request structure or status structure of the target, for example. And then we have a header data field in some of the formats to provide a path for out-of-band information when the providers need it or the upper-level loggers need it. So just to go through that in pictures a little bit, the left-hand side here, you see kind of standard Ethernet framing. The specific one builds up a Rocky V2 frame example. And on the right hand, we have the slingshot framing. So we did some things at the link level. So when we're talking to slingshot devices, we can reduce the preamble and eliminate the interframe gap. That preamble that we have, which is kind of half the standard Ethernet size, also includes the information needed for link level retry. We compress the address information to reduce the kind of overhead at the front end of the packet for figuring out where the packet goes. And then we have specific transports for PGAS, for matching operations, and then for continuations. So continuations are subsequent packets associated with a large message transfer. So there's a header that carries the information about where it's going to go. And the continuation has a lighter weight header overhead on it. At the bottom here, you can see a comparison of kind of what it takes in terms of header overhead and other framing overhead for SHMEM put. So we can do 40 bytes of header plus framing total. That's everything. Everything that's on the wire is 40 bytes of overhead. And then for the MPI case, it's only 57 bytes. So we have an address translation engine. Let's see. For the sake of time, I'm going to go through this quickly. We have both the PCI Express ATS mode with PASID. This is kind of the standard infrastructure that's provided by PCI Express for obtaining address translations. We also have a native translation mode, largely because not everything has an ATS implementation, and if it does, it's not always a great one. There's other advantages, like sometimes page sizes bigger than 2 meg but smaller than gigabytes are actually a sweet spot for translation cache efficiency as well as usability. So you can get kind of conglomerated together 32 megs of stuff into one translation. A lot of times it's harder to do that with the gigabyte pages. We do hardware matching, and the reason for that is that a lot of apps, real apps, don't hit the head of the list. Sometimes real apps even have unexpected message. Actually, a lot of times real apps have unexpected messages. And so we wanted to sustain a message rate even in the presence of a posted receive queue in MPI. So you've posted more than one receive and you have to traverse down it. And so we targeted 6.4 billion match attempts per second. That's 64 match attempts per message at 100 million messages per second. And if you think about what that would mean on a CPU, it would be an enormous load. Assuming those were misses in the cache, that would be something like 400 gigabytes per second of bandwidth that you burn through. It would be hundreds of billions of instructions being executed. And we'd rather leave the CPU off doing computing than doing that matching work. We implemented that with 4 matching engines, each of which had a context to provide some additional concurrency. We can traverse a match list entry in only 4 cycles. So there's essentially a hardware implementation of match, and that latency is what it takes to walk down a linked list item. Each endpoint in libfabric terminology gets its own queue. A process can have multiple endpoints, and so each of them is independently queued, and then you can schedule from the head of any of those queues, so you don't get cross-blocking between processes as they try to use those matching engines. So just some quick performance results from that. As we vary the number of match attempts here on the left, with PPN number of processes per node going up the stack, we only ran it up to 48 in this case. It's a little bit older data. And you can see that those graphs are flat out to around 64 match attempts per message, and then they start to tail off as the time to traverse that much linked list starts to eat into your message rate. But it's a flat message rate out to 64 match attempts or so. Right-hand side is 64 processes per node, and is just graphed against message size, and you can see a nice flat graph there. And again, that's right at 100 million messages per second, attempting 64 matches per message, is flat all the way out until its bandwidth saturates. We did a number of SHMEM optimizations as well, because we had this transport that's really low overhead. If you kind of do the math on that transport, your one-way message rate theoretical caps out at around 500 million messages per second. That's a lot. Actually, PCI Express won't quite sustain that. But we did a lot of work to enable the NIC to process messages on both transmit and receive side at that rate. So for example, on the hardware, at the target, instead of going through a matching engine, it will actually detect that you've got a case where you have a simple endpoint. And by simple, I mean that you have a single non-matching memory region at the start, and it will bypass the matching engine and use a simple table lookup to get the state for that. So you can process those messages once every 2 cycles as they're coming in. We accelerate the synchronization for PGAS as well, Cassini. So we actually have a fence command that will block further operations for a given transmit queue until older operations have completed. We have counting events, which are a very lightweight way to track completions. We have remote flush operations, and this helps us with our multi-NIC operation because we have multiple NICs per node in a lot of those pictures. It also helps with the interaction with a lot of the different memory systems. So if you look at GPU memory systems and how NICs interact with them, there are some ordering challenges there that are solved with remote flush operations. We have a wide range of atomic operations. So we support 8, 16, 32, and 64-bit integers. We support 128-bit integers as well for some operations. We support both 32 and 64-bit floating point, including complex operations for a couple of operation types. We have logical and bitwise and arithmetic operations across all those types, and a variety of compare, swap, and mass swap operations. A quick SHMEM performance side. This is put rate on the left and get rate on the right. There's 2 lines here on the left. So this is 64 ppm. There's 2 lines. The top line in this graph uses a feature of libfabric called FI more. FI more is a way to tell the library that more stuff is coming. Now, what we use that for is to improve the provider so it reduces kind of the overhead inside. We do not use that for message aggregation because message aggregation doesn't scale when you're targeting tens of thousands of other SHMEM-PEs. And so we don't use that for message aggregation, but we do use it in the interaction between software and the NIC, kind of eliminate doorbell rings and things like that opportunistically. And so we're able to get a bit more rate by doing that. And we're looking at how to introduce that into OpenSHMEM, or introduce capabilities that would make it easier to use that to OpenSHMEM. We are still working on the software optimization, but you can see here that we're well over 200 million messages per second. In the default case, we top out over 350 million messages per second using FI More, and that's out past 64-byte messages where it starts to taper off because it saturates the bandwidth. Great, it's up near 180 million messages per second, which is a pretty solid get rate. We don't have FI More implemented for that yet. All right. Another important feature of Cassini is the support for triggered operations. Triggered operations have existed since the Quadrix days. They were expanded in Portals 4 somewhat. It's really a generic programmable small message operation kind of capability. Research has shown them to be not quite Turing complete, but getting there. And so there's a lot of things you can do with trigger operations, and we encourage people to take a look at them, develop new algorithms. If you have a good idea for how to use triggered operations or an extension to triggered operations, contact me, because this is something that we're actively developing and extended. Cassini provides the hardware to hold triggered operations, the state for them, to automatically trigger them when an accounting event reaches a threshold. You can count local completions, remote completions, or both. And we can trigger basically all of our standard HPC operations. All right. A slide, Cassini is our exascale end-to-end NIC. We've gotten great performance out of it on Frontier. It enables us to get new levels of interoperability with the data center, which is a big change for HPC systems because, for example, you can speak Rocky straight off of a Cassini NIC out to a storage system that's sitting out in the data center. Oh, wait, one more slide, bonus slide. So this is the this is Cassini 2 on the right here. That's our 400 gig part. It's also a dual NIC part. It'll have PCIe Gen 5 and 400 gig E on the network side. All right, just in time.
Keith, thank you very much for a very interesting presentation. Very informative. For attendees, if people have questions, please post questions on the Slack channel. As for now, I don't believe I see any posted questions.
There's 3.
Okay, there's a few. There's a few. Okay, I will read out because I wanted to use the opportunity to ask my questions, but.
Oh, go ahead. Ask your question. I'll ask the
answer. It's fine. We'll start with Rahid. Question from Rahid: how many OFI endpoints can one create per Cassini NIC?
Target side endpoints is 2,000.
Okay.
Transmit side endpoints, you can, depends on exactly how you want to multiplex things. You can do better.
A question from Kevin: does Cassini NIC only work well with Rosetta slingshot switch, or it can be used as a general, general use NIC? Is there any drawback to GPUs?
Oh goodness, you know, we've only really tested Cassini in an environment with Rosetta. And so I would not recommend plugging it into an arbitrary switch. But in terms of you know, general purpose use like speaking IP and Rocky, you know, we don't, our offloads for the TCP stack, for example, are not as aggressive as some people's at this point, because, you know, we're an HPC NIC first, and we're a TCP NIC second. And so, we'll have more CPU overhead for that path than some might, but it's still a pretty solid path.
Okay, next question is from Manju. Is remote flash tied to any particular memory bus or interoperable?
So the Cassini connects to PCI Express, and so a flushing operation on PCI Express is simply a 0-byte read, and so the transport will let us communicate the need to do that, and so that works with anything that honors the PCIe ordering semantics for a 0-byte read.
Okay. Makes sense. And now I have opportunity to ask my questions. I have a couple of questions about tag matching. Does it support wildcards? And follow-up question, does it support multi-rail?
Wildcards, yes. It does support wildcarding for all the standard fields that can be wildcarded. It actually the match structure that it exposes is very much like libfabric or like portals, where there's a set of match bits, as well as an ability to match on initiator information and to wildcard that. Multi-rail, right now we don't have mechanisms in place to distribute one message across multiple rails. If you look in most systems these days, those NICs tend to be plugged into very different places in the memory hierarchy, and you tend to need to have a good bit of concurrency in the node to use what those nodes look like. And so it wasn't really worth the effort to invest in putting a single message across multiple rails, because they would be coming from different parts of the memory hierarchy that were kind of better serviced by a NIC that was closer to that part of the memory hierarchy. And then we expected, if you have a multi-GPU system, you're going to have, you're most likely going to have multiple ranks on that system.
Okay. What about like different types, like you have shared memory communication and let's say slingshot communication? I guess in this case, tag matching is disabled, or you have to go also slingshot, right?
We do actually support on-node transfers through shared memory, and the details of how that stack works. I didn't prep for that question, so I'd have to go back and look. But I know that I know that we do have that enabled in production to do on-node shared memory transfer as well as slingshot transfer between nodes.
Thank you, Keith. We have one more question. In your testing, how does the Cassini NIC plus Rosetta switch compare in latency to the older ANC HSN from HPE Cray?
I don't have those numbers hand. Sorry.
Okay.
I'm a short timer at Cray. I was at Intel before this, and so that was ancient history.
Okay, thank you very much, Keith. Really interesting talk again. Thank you for presenting today, and we'll be moving to our next talk. So let me check if we have next speakers online here. Do we have Jaime or Ravi? I see Jaime online, but he's not a panelist. Let me see if I can promote you to panelist. Hey, Jaime, you should be able to unmute and share your slides now.
Mute. Hello?
Yes. So we can hear you.
Yes.
Jaime, do you want to try to share your slides?
Yes, so start video. Where do I go?
You
No.
should have share screen option.
Ah, share screen. See it. Am I sharing?
Not yet. Let's
Okay.
give it a second.
So let me know when the screen is seen.
I can see the screen, but I also can see Microsoft Windows bar at the bottom. Make sure you're in
Okay.
the presenter mode.
Sorry, say again.
Make sure that you're in the presenter mode. Okay, it still shows. Anyways, let's.
Where is the presenter mode here?
No, I think you use the right button. For whatever reason, still keeps the bar. Anyways, let's go with what we have.
Okay.
So our next talk is by Jaime Arteaga and Ravi Ganapathi. I don't believe we have Ravi on the
Yes,
session now.
he's on the Slack channel.
Okay, Ravi on the Slack channel. Jaime is a graphics software engineer at Intel, working on development of Intel oneAPI drivers for Intel GPUs. Previously, Jaime worked on Intel Omnipath and performance optimization and development of front-end libraries, enabling libfabrics transports. And Ravi is a technical lead engineer manager responsible for technical leadership, vision, and execution of Intel oneAPI level 0 drivers for Intel GPUs. In past, Ravi led development of Intel Omnipath libraries, including enabling libfabrics. He also lead developer and architect for Intel Xeon Phi offload compiler runtimes. And Jaime, the floor is yours.
Okay. So thank you very much for the introduction. So yes, so me and myself and Ravi, we work at Intel, and currently we're working in the development of the oneAPI level 0 programming model and library. And what we wanted to show here is the current state of this. This is a new programming model that Intel has designed, and we are kind of communicating with the community. And we thought that this was a very good forum to share. So we're going to show first what level 0 is, the motivation behind it, and the main APIs and top-level view of the programming model. Then we're going to talk a little bit more about the scale-up, which is more relevant to this audience, which is pretty much the capability that level 0 is offering for GPU to GPU connection within the same node. And finally, we will talk about a summary and next steps in our current work. What is the motivation behind level 0? The main motivation was that, as you guys have seen from news articles and other talks, I guess, Intel has been pushing right now for the development of GPUs, of an ecosystem with discrete GPUs. In order to have that hardware, Intel was also was desired also to create the software stack to support that hardware. And the main component of the software stack is level 0. Level 0 is designed to be a low-level thin layer at the bottom of the stack. So it sits right in the bottom of the user space, right above the kernel. And the main idea is to provide all the tools that middleware libraries applications need to extract the most performance of the GPUs or the accelerators, because level 0 is not only aimed at GPUs, it's aimed at any kind of accelerator. One of the other objectives here in level 0 was to have much more control of the cadence of the API. So if there is a new hardware feature, if there is something new that we want to add to the spec, to a new interface, we can add it as soon as we want, and we can have like a much better process of releases that match those releases of hardware. Finally, of course, we have features like function pointer, virtual functions, unified memory, which is the memory model in level 0, I/O capabilities, and peer-to-peer that, as I mentioned, we're gonna go deeper in a later slide. Level 0 is completely open source. So even though it is originated at Intel, all the specification and current implementations are in public repos. The links that you're seeing in the slides are first the spec, the definition of the spec, the loader. For those who are familiar with OpenCL, in OpenCL you have a loader that is pretty much a device vendor agnostic module that loads all the drivers in the system. This is something similar. Ideally, in the future, you could have level 0 implementations for GPU, FPGA, and other accelerators in the same system. The level 0 loader is the module that is in charge of finding those modules, those drivers in the system, and then link them to the application. We have the level 0 Intel GPU driver that is our main implementation of the spec at this moment. And this is the driver that we are implementing to support all the Intel GPUs that are in the market. And finally, we have 2 repos for conformance and performance tests. And of course, the conformance tests are used for if anyone wants to start implementing the specification on its own drivers, devices for its own company. We have the conformance test so you can know if you're being compliant with the specification. So this is a high-level view of the level 0 APIs. So as I mentioned, the level 0 API sits right above the kernel, and we have different types of accelerators, GPU, FPGAs, AIs, etc. And on top of level 0, you could have middleware libraries, high-performance libraries. In the oneAPI ecosystem, that is the software programming model that Intel is promoting for the Intel GPUs, we have SQL and OpenMP sitting above level 0. So when you use SQL or when you use OpenMP with a Intel implementation, at the end you're calling level 0 to be able to use the Intel GPU. Inside level 0, we have different APIs for different purposes. We have basically 3 APIs, Core, Tools, and Sysman. The core APIs are the main APIs to be able to use the GPU. Discovery of devices, submission, synchronization, allocation of memory, allocation of resources, all that is comprised in the core APIs. We have Tools APIs that is mostly for reading performance counters in the GPU to have analysis of debug, for instance, debugger capabilities. And we have finally Sysman, which is the APIs to be able to control the system and the GPU. We have APIs there to read power and set the power, read frequency, set the frequency, read the fabric and the topology, how the GPUs in your system are connected, etc. All those are part of the same level 0 specification. It's just subsets of APIs. In the compute or core API, what we have is the main objects or classes that are on the right. So we have drivers, we have contexts. Contexts are basically what you use to separate resources in your program. You could have two different contexts with different objects or resources. Besides that, we have host and device and shared allocations. These allocations are part of a unified shared memory system. Anything in level 0 is part of the same unified virtual address space. And idea is that the same address and pointer can be shared between host and any GPU to be accessed. We have command queues and command lists. So command queues is a software concept that has a corresponding physical stream in the GPU or accelerator. So for each physical stream or input stream that you have in your accelerator, you have a command queue. And we have command list, which is a purely software construct. And a command list is a set of commands that you create and you have it ready to submit to any command queue. So command list is just a group of commands that you can submit to any input stream in your accelerator. We have fences, events, and event pools for synchronization. And finally, we have modules, kernels, to facilitate the use of GPU kernels from the application and users. Okay, so in the core API, like I mentioned, core API or in level 0, you use that to communicate to the GPU or the accelerator what you want to execute. You're able to discover your devices, allocate memory, submit something for execution, and then synchronize pretty much. That's the general flow of your application. But in addition to that, you can do that execution. You can do that synchronization. You can do copies if that's what you want. You can do it not only between a host and your accelerator. You can do it between two accelerators or pretty much peer-to-peer access. And that's what in level 0 we call a scale-up. And it's the implementation that with which we allow GPU to connect to other GPU, either, for instance, through PCI Express or through XC-Link. XC-Link is the high-speed fabric that is proprietary to Intel that we expect to have with the PVC devices. In the previous talk, you saw that Kit showed in one slide how the Aurora system is going to have on a PVC when he was showing. Those links that were connecting through each PVC is an XC-Link. And the implementation of a scale-up that we have is based on Linux DMA buff. So the idea here, as mentioned previously, we want everything to be open source. So all the mechanisms that we are using, even to implement a scale-up, to implement peer-to-peer, is purely open source. So there's nothing proprietary here other than, of course, let's say the manpower to write the code. But when you go and see the code, when you see which are the basic mechanisms that we are using, those are open source, including DMA buff. Finally, even though here we're focusing only on talking about the scale-up, peer-to-peer, GPU to GPU, for instance, these are the basis for communication between GPU and other nodes. That means going through the NIC. And that's what we call by scale-out. So scale-up within the same node, GPU to the other GPU in the same node. But if I want to have connection between a GPU in one node and another in a separate node, then we have a scale-out that is other work that is happening in parallel, where we use the NIC to go through the wire. And in this case, actually, we are also using lead fabric, which was also mentioned in the previous talk. So how a scale-up works with level 0. So for those that are familiar with OpenCL, there are some APIs there like SIM analog device, append memory copy, and others that are very similar to those that you find in other GPU programming models. In this case, what we do is that level 0 creates two allocations in the GPUs, thanks to or after the application has called sim analog device. That goes through level 0, that is called the UMD, or user mode driver. And then the requests go down to the i915. i915 is the kernel mode driver that controls the Intel GPUs. And thus, those i915 or kernel mode drivers create an actual device allocation or buffer object in the GPU. In this case, in this sample, we have 2 GPUs. Each GPU has a different i915 or kernel driver. Once you submit a pen memory copy operation that, for instance, we also have a counterpart, for instance, in OpenCL is CLNQ write buffer. This is very similar, it's a memory copy. The user mode driver or level 0 identifies that one of the pointers of that copy, either destination or source, are in another device. So we are executing in one device, but one of those pointers is in a separate one. Internally, level 0 creates the DMA-BOF handle with the i915 and makes all that is necessary in order to pass it to the other i915 and being able to access it. When one of the i915s receives the DMA-BOF handle from the other i915, then it recognizes that it needs to do like a handshake. So one i915 communicates with the other in order to be able to use the same physical allocation for the original device allocation. So there are no intermediate copies, there is no bounce buffering in the host. The i915 that receives the DMA-BOF handle interacts with the other i915 to be able to access the original allocation. And that happens, of course, through DMA, the memory access. So once we submit the copy operation, for instance, here to the execution units or compute units in the GPU, there's no more host interaction. There's no UMD application. They don't need to do anything. Automatically, one of the EUs in the EUs in one of the GPUs will access directly the device allocation in the other. A scale out is going to be something very similar, where by using the DMA-BOF handle, we can export the device allocation to the NIC driver, and the NIC driver will be able to access directly using DMA to that device allocation and then pass it to the other node. And that will happen without any host interaction again. Implementation of this is already in public. If you go in one of the repos that we mentioned in the other slide, you're going to see that support for this in the Intel GPU driver is already there. And one of the tests that we have been using to validate this functionality is called ZPeer. Going back to OpenCL, because that is very familiar, that is very common for some in the community, we have CLPeak. CLPeak is the first thing that you use sometimes when you have a new GPU and you want to measure the performance. The same objective is that we are trying to have with ZPeer, to have a standardized test that you can use to test the connectivity within your system, within the GPUs in your system, and check, for instance, what is the latency, what is the bandwidth, what happens if you use different types of engines or streams in your system, what happens if you use a push or a pull operation, etc. The code is public there. And like I said, this is the main test that we are doing for bring up any system that has multiple Intel GPUs. This is just a screenshot of the different options that we have. Anyone is free to download it, build it, and if possible, to use it. Now, this is a synthetic benchmark, and it has been used, like I said, this is mostly used to confirm what is that your system is capable to give, if your system is ready for scale-up. But as such, this is just that. It's just a benchmark and tells you the capabilities. However, the interesting part is when this feature is used by high-level programming models. by actual applications. And actually, a scale-up has been started to be used by oneCCL and MPICH. oneCCL is one of the libraries in the oneAPI stack that is being designed for high-performance collectives. So oneCCL is Communication Collectives Library. And that library is already calling level 0 directly, has that implementation to be able to offload the collectives to the GPU. So an all-reduce operation is not performed the host. oneCCL just detects the number of GPUs that are in the system and offload the all-reduce. And when you are doing the all-reduce or the broadcast, whatever, all that happens thanks to the peer-to-peer scale-up feature in the Intel GPUs in level 0. Something similar is happening with MPICH. So MPICH is, of course, one of the major distros for MPI. And in this case, MPICH does something similar. It detects if level 0 is there, and if it is there, if it has a scale-up or a peer-to-peer capabilities, if the GPUs in the system can access each other. And then what it does is that implements all the collectives, all that it can in the GPU directly. Besides that, MPICH uses the IPC mechanisms that we have in level 0 to exchange device allocation not only between GPUs, but between processes. And more than that, not only to go within your same system, but also to go through the wire to other nodes and exchange those DMA buff handles with the NIC driver, calling internally lead fabric. And that's also other part that is being used right now. So Big Fabric, part of the Open Fabric interface, as in the previous talk, it was also mentioned. Lead Fabric already also has support for level 0. That support is being added, and support to use a scale-up and a scale-out. And the same basic mechanism that we just mentioned before is used here. Pretty much, Lead Fabric or MPICH accesses level 0, requests device allocations, and then requests the IPC handles or the DMA buff handles to be able to exchange that device allocation with other NICs or with other devices. With oneCCL and MPICH and Lead Fabric, I guess that is still there's work going on, but in public repos of those libraries, you can see already level 0 interfaces. It's not a finalized product, but you can see it. Okay. Of course, what we wanted here to show has been mostly an introduction of this. We don't have at the moment yet performance data. We don't have at the moment how much bandwidth we can leverage, with how much latency we have between GPUs. But that's a work that we are doing right now. As soon as more Intel hardware or hardware with those capabilities becomes available. But the main idea that we wanted to show here is that there's a new programming model that Intel is designing, that Intel is implementing, and that actually we are sharing with the community. So we already have meetings with some people outside Intel, from academy and national labs and other institutions, that they are already implementing level 0, or they are using our implementation of level 0 for their systems. And we are already having those public meetings where we have discussions about new interfaces, what can be added to the spec, how we can improve either the execution model or the memory model. And as we move forward more with those feedbacks, with those comments, and with hardware availability, we hope to be able to showcase more what the level 0 and Intel GPUs are capable of. And yes, there are some links here, and you can see these are the links to the oneCCL, MPICH, and Lead Fabric implementations. Okay. I think that I did it on time, but of course there are time for Q&A, or I don't know if we have time.
We do have time for a couple of questions.
Okay.
First of all, thank you very much for presenting this, Jaime. Really interesting overview of oneAPI level 0. For attendees, guys, please use Slack channel to ask the questions. And I will pop into Slack and see if they have anything pending. I don't believe we have any outstanding questions. So one question I have then, you mentioned integration with MPH and the Fabric. What about integration with other MPI implementations like OpenMPI? Do they get the support for this automatically through libfabric, or it has to be implemented separately?
So most for MPIS, there is implementation inside MPIS, right? To call directly to level 0 and then to use libfabric. To add support for MPI, we will need also some kind of support. Yes. I don't know if that is in progress, but certainly that is something that we hope that in the future we will have. That we will have some kind of support on OpenMPI. But yeah, most likely, and I would expect that there should be some kind of changes in the OpenMPI code in order to support it.
Okay, thank you for answering this. Let's check the Slack again. Guys, don't be shy. Please ask questions in Slack channel. Okay, I don't believe we have any outstanding questions. Thank you again for presenting this.
Yeah, of course.
I really appreciate this. So I think if I look at the schedule, okay.
Great, please go ahead.
We see your regular slides, not the presenter mode. So if you can enter presenter.
There you go.
Yep, it's excellent. Okay. So the next talk we have by Elad Alon. The title of the talk, Bunch of Wires, and Open and Versatile PHY Standard for Die-to-Die Interconnects. Elad is technical lead of the ODSA Bunch of Wires PHY working group, as well as the CEO and co-founder of Blue Cheetah Analog Design, which is leveraging a decade of research and development on generator-based design methodologies of rapidly delivering tailored AMS designs to meet customers' diverse needs. Elad, the floor is yours.
Great, thank you very much. So thank you all for the invitation. I'm very happy to be here and have the opportunity to speak to you all. So as hopefully you can tell from the title, what I'm presenting today is about the bunch of wires, or BOW. And in particular, BOW is an open PHY specification for die-to-die parallel interfaces. A few of the key features in bunch of wires is that it really is optimized both for commodity, specifically organic laminate packages, as well as advanced packaging technologies. It's compatible with a wide range of packages and IC processes. And it really does achieve state-of-the-art performance metrics, which I'm trying to highlight and really summarize with that table on the bottom right there. So you can achieve up to about 1 terabit per second per millimeter in an organic laminate package, and in the 5-ish terabit per second per millimeter in the advanced packaging technologies. Well sort of under half a picojoule per bit in the organic and under the sort of 1/4 picojoule per bit in the advanced packages. Error rates low enough that in many applications one doesn't necessarily need additional error correction, and reaches kind of commensurate with the types of packaging that you tend to see here. So up to about 25 millimeters in the organic case and up to about 5 millimeters in the advanced packages. And certainly from a latency perspective, which is one of the key requirements in many applications. I'll say some more about that a little bit later, under about 2 nanoseconds for the PHY itself. So one sort of important thing that I wanted to just sort of highlight here that you see as a recurring theme throughout the talk, something that was really taken to heart from a approach in designing the specification is that we really want the die-to-die interface to be able to be optimized to the specific host chiplets and the products that these interfaces are being used for. And so particularly, there's really a minimalist approach that was taken to the features that are required in the standard to enable interoperability, but are not actually, essentially, we really don't want to expand beyond that at the risk of essentially causing extra overhead for any one particular implementation. So just to sort of explain a little bit what the basic organization is, and this is mostly just to define some of the terms that I may intentionally or unintentionally refer to a little bit later. The basic unit in BOW is what we refer to as a slice. So slice is simply 16 data wires, a source synchronous differential clock, and then optionally a so-called FEC bit for error correction, and an auxiliary bit that one may use for things like data bus inversion or repair or framing, things of this nature. Now, this is already hinting a little bit some of the intentional flexibility built into the specification. So that unit element, that slice, can actually be arranged in multiple different ways. One can stack, which is essentially a way of increasing the bandwidth density for a given chip sort of die edge by essentially extending these slices inwards towards the center of the chip. And one can build a link, which is essentially one or more slices that are serving together as a logical unit to meet the needs of some higher level application. And these links, by the way, may be symmetric, asymmetric, unidirectional, right? There's nothing in the specification that requires them to be one way or the other. So just to touch again on a few of the key features that specifically were designed into the specification for interoperability as well as for flexibility. First of all, and I think a bunch of wires was the first sort of standard that they kind of took this approach. We really only require an order of wires on the package, but not a specific bump map. And so the idea here is that even though there's a recommended bump map that most people will likely adopt just based on sort of ease of integration and design, as long as you follow that same wire order, you can actually get things that are interoperable, even if there's some differences in bump map, some differences in bump pitch, and things of this nature. Another sort of similar approach is that we said, okay, well, to really support a broad range of process technologies, we want to choose an I/O operating voltage that is very likely to be supportable by a broad range of processes. And 0.75 volts is, I think, a very reasonable choice from that perspective. So this is the I/O voltage that is required for all implementations to support. But any particular implementation or system is free to use other voltages, specifically to essentially, do appropriate optimizations and trade-offs between performance, BER, and reach. Of course, as long as the PHYs on the two sides from a datasheet perspective are able to support that same sort of, operating voltage. Similarly, and again, this is really just sort of a little bit of a preview for some of the flexibility that's intended to be intentionally handled here. The slices themselves are specifically defined only with serialization to serialization. And no, let's say, explicit clock domain crossings are required within the PHY. And the reason for that is, again, that the need for sort of, various types of clock domain crossings, particularly things like, asynchronous or isochronous FIFOs, are actually somewhat usage dependent. There are applications where one really does not need those. And so essentially, kind of following that philosophy that I mentioned at the beginning, the PHY specification does not require it, and that allows these decisions to be made outside of the PHY, where somebody tends to have a better knowledge of the real needs for a particular chiplet application. And similarly, you can imagine, there are cases where if you really can skip these extra clock domain crossings, that's quite beneficial from a latency perspective. So again, this is just something that's done to allow for that absolute lowest possible latency implementation. So another piece that I wanted to just sort of briefly highlight, I personally actually spent quite a bit of time and effort on this side, but along with a lot of work from many members of the community, is that there's a quite detailed set of electrical and timing requirements that are included in the specification. And the point here is not to say that, this is, not to say that essentially that, flexibility is lost by having these detailed requirements. They're really just there to ensure that, that PHY designers know quite specifically what are the bounds of things that they need to be able to achieve. And things really are done in a way that it's clear that, here's where things have flexibility and here's where essentially, the bounds really must be met on a particular parameter. So I won't walk through kind of the details, unless there happens to be other kind of circuit design nerds in the audience who want to ask. I'm more than happy to talk about that. But I will say that these specifications were really developed based on community contributed channels that are essentially real mock-ups of actual channel designs that people would be interested in, that were then taken through very sort of detailed and complete by characterizations and signal integrity analysis, as well as basically experience from in-flight designs of essentially various people that were working on implementations at the same time as the standard was being developed. So again, the point here and really the goal is to provide clear and detailed guidance to people who are implementing the FIs, but at the same time, allowing them degrees of flexibility to perform the optimizations they would need to do to reach the overall best solution for the given application they have in mind. So very similarly, channel conformance in bunch of wires is specifically defined really only by the performance achieved on a given channel using reference transmitters and receivers. And so again, the idea here is that somebody may have a very different and very innovative way of building up a channel, which we may not have even conceived of yet. And as long as essentially it meets a certain set of effectively timing margins based on evaluations using essentially a detailed signal integrity software, then that would be considered a conformant channel from a bunch of wires perspective, and everything essentially will work from an interoperability standpoint as long as these needs are met. So I will mention that open source software for essentially doing that conformance checking and the system simulation will be released in the near future, contributed again by members of the community. I'll also mention that there's actually multiple reference channel designs and models along with all the associated SI analysis results that are publicly available. So one can go and actually download the reference packages and sort of use that as a beginning point for any actual real design, go through all the SI analysis, all the assumptions, all the sort of characterization that was done to really sort of boost the confidence that indeed this is a deployable and usable approach. So very much along those lines, obviously a key point in having an open standard like this, and really perhaps the main reason for doing so, is to allow interoperability. So unlike in perhaps like the board level world where you can just go and literally do a plug fest, or you take one board, plug it in, you unplug it, put something else in. Here obviously these are in package, so pluggable is not quite the same concept. But nonetheless, demonstrating that interoperability, really is a very important step for sort of driving forward the effort within the community. And so actually I'm happy to report that there is a community-driven effort that essentially the whole intent here is to accelerate the adoption by really showing that multiple independent vendors, essentially following the specification, can actually put chiplets together and put PHY implementations together that will be able to successfully interoperate with each other. So I'm just showing a little bit of a snapshot here of the community designed package that's contributed by one of the members of the working group that's essentially taking test chips from, again, 2 different vendors, Blue Cheetah being one of them, D-Matrix being the other. 2, again, sort of entirely independent PHY design teams, both obviously involved in the development of the specification, but neither one of them having sort of, let's say, a particular insight into what the other is doing beyond that. And so this test package is something that essentially will be ready and begun to be tested by essentially the end of this year or very beginning of next year. Again, just to sort of show this multi-vendor interoperability. And again, this is with some silicon packages and everything of this nature. So just to touch a little bit further on kind of the adoption that's happened so far, I think Bunch of Wires has gone through a somewhat unique development cycle in that it really has been open, sort of to the community to participate and contribute from the very beginning, and drafts have been available also from the very beginning. And so from that perspective, there's been a lot of, I think, both adoption and acceleration in terms of the ability to actually go and build real designs, simply because, this is something that, was always open and available to the public, right from the get-go. Specification was formally approved and released just a little bit over a month ago. I can point folks to sort of further announcements on that if you're interested. But I think the more important point is that an ecosystem around Bunch of Wires really has already formed, and is actually Bunch of Wires is being designed into products essentially today. So there are known PHY implementations from a number of different companies in 65 nanometer, 22 nanometer, 16 nanometer, 12 nanometer, 6 nanometer, 5. In fact, there's even a couple more that we're not explicitly listing here. So you can see it's actually covering, as I said in the beginning, a very broad range of process technologies. And that's really sort of reflecting the fact that we intended very specifically for the specification to be usable across the broadest range of applications that's possible. I won't, sort of go through the full list of the companies and the products here, but there are over 10 products that are indeed already being built using BOW. There's a number that we're aware of that are not sort of out in the public world and domain just yet, but there are indeed quite a few here. And I'm just sort of this is really more eye candy than anything else, but just showing you a few sort of snapshots of sort of artifacts like test chips or test packages or sort of product, sort of say chiplet plans that are built all around a bunch of wires already. So from a roadmap perspective, I wanted to touch on a couple of things. In particular, I want to sort of highlight that there's actually already an open standard in draft format for today, but will be approved formally fairly shortly, specifically for a lightweight link layer that is, again, very much targeted at the die disaggregation market. And when I say that, what I specifically mean is that typically in most die disaggregation markets, there's some on-die bus, in many cases, probably in most cases, an AMBA bus. That essentially, what you're trying to do is take things that otherwise would have been communicating on that on-die bus, essentially splitting them into multiple separate chiplets. Now, what's really important here is that from a latency perspective, these are things that really need to be in the single-digit nanoseconds. And so one really has to build the link layer and obviously how it interoperates with the PHY in a very specific and targeted way to ensure that you can keep those latencies to an absolute minimum, because you're starting from the on-chip world. And so therefore, so that's something that people are very, very sensitive to. So there's a layered approach that was taken here. I won't dive into too much detail, but I'm happy to sort of take any questions if there are, where essentially there's core link layer functionality that's defined that's largely independent of the specific bus or protocol that one is interoperating with at the sort of chiplet level. And there's transaction layers that essentially do the matching between the internal services offered by the link layer and the actual protocols of the buses behind them. And this is where you sort of are able to do furthermore, this is where you further gain the ability to essentially have sort of optionality and configurability in terms of the different, let's say, specific fields and widths and definitions of any given on-die bus that you're using. Because I suspect many of you know already, if I say that something is, for example, a CHA bus, that's not a unique definition. There's actually a bunch of optionality that is embedded into that standard simply because, once again, in a sort of ASIC or chiplet implementation, there's many optimizations that people tend to need to do for either performance or for functionality or cost. And we want to be able to reflect that all the way through in the data interface as well. Furthermore, I will say that the development of the sort of a revised version of the bunch of wire specification, where really the primary target is to just add in a few key feature extensions to really enable certain specific targeted applications beyond the original spec, is actually very much well underway. So we have some new schemes that are essentially being written into the standard in terms of how to do fine-grained clock gating without actually influencing or impacting the bandwidth density at all. Sort of pushing up on the data rates, really mostly to push for the very edge of the sort of bandwidth density limited applications. Something one has to be really cognizant of here is just the energy and efficiency implications of that. And there's some essentially schemes that we're working out on how to achieve that, and again, pulling out the power budget too badly. And then finally, for a number of other sort of, again, optional features, just to, again, sort of match certain application niches that need them. So things like reduced bit widths, redundancy, and sort of defining things that may be used specifically for bring up, as a sideband. These are all sort of optional extensions that are being built. And as I said, are actually quite far along from a definitional standpoint that are being baked into the standard right now. So just to summarize, what I hope to have kind of described and give you the taste of here is that bunch of wires really was very uniquely designed to allow adopters and implementers to select and trade off between essentially varying sort of characteristics from a packaging, process technology, performance, and even complexity standpoint without actually having to switch to a different data standard in order to achieve that. And I do want to highlight that a bunch of wires is it's out there now. It's very much available. It is really being actively adopted, very specifically in many cases for the die disaggregation application. And as I've kind of touched on a few times, I think a really key enabler here has just been the fact that BOW is essentially a fully openly licensed, and openly available. So there's no NDA, there's no signature, there's no sort of other sort of click-throughs or anything like this. It's just, you can go to the website, download the spec, and essentially, you're free to do with that as you please. So, the last kind of piece here is that I would certainly like to encourage everyone to participate in any way that you'd be interested to. So as an example, there's going to be an ODSA session at the OCP Global Summit in about 2 months from now. So please do come and attend. You'll see a lot of interesting and exciting developments there. If you want to participate in the test package Plugfest, either the development of that, or perhaps you have implementations that you don't want to sort of come and contribute and see how we can sort of go and test the interoperability. Again, we very much welcome that. Everyone is basically entirely welcome to join the working group and provide feedback or to drive the future specifications. And if anybody would like some more information, I just have sort of various links here that I'm pointing to. Both the GitHub repo for the PHY specification, the GitHub repo for the link layer specification, and you can sort of see just more information about the ODSA project as a whole with that last link here. So with that, I'd like to thank you all again for the invitation and for your attention, and I'd be very happy to take any questions.
Thank you very much, Elad, for the talk and for the presentation. I lost the window, but I saw one pending question from Davide. He was asking, compare and contrast this standard to UCA.
Yeah, that's the question, of course, that we very much expected. So I will first say that, myself, as well as I think, everyone in the working group is very much supportive of, any efforts that, expands the chiplet community. I think there's very much a shared vision in terms of enabling chiplets to operate with each other and really change the way that the semiconductor industry can kind of do business, from an open chiplet market perspective. I think, there's obviously a number of kind of detailed specifications that, I'd be happy to, have a further discussion kind of offline. But I think the biggest differentiating factor is really sort of in this approach of attempting to match the die-to-die interface to the needs of the individual chiplets, and essentially allowing that flexibility and that optimization so that essentially you can really sort of plug these things in and retain much of the flexibility that you would have had, had you been doing everything fully in an integrated format. And that's really very critical, in particular for the die disaggregation space. And so I think that's, sort of at the moment, that's really a primary differentiation. Also just in the sort of, fact that, there is a sort of interoperable and open specification for how to do specifically these AMBA buses with low latency. But essentially those, I think, the really the primary factors from a high level standpoint that are going to cause BOW implementations to potentially look different than what a UCIe implementation might look like.
Okay, thank you very much for addressing the question. There is few more questions in the chat that I believe already were in Slack channel that already were answered. So I'm not going to repeat those questions. You can jump in the Slack channel and read it. And in sake of saving time, I will jump to the next presentation. Thank you very much again, Alon.
Thank you.
And the next presentation is video recorded. And let me try to share the screen and you guys will let me know if you can see it. Can please somebody confirm that you can see the slides?
We can see, Ash.
Okay, then I will read out the introduction. The next speaker is Chad Markey, Synchronous and low latency die-to-die interface for the IBM Z16 Telum processor. Chad is actually available online as well and will be monitoring the Slack channel, answering questions, but the presentation itself video recorded. Chad has been with IBM System in Technology Group in Austin, Texas since 2016. He has experience with electronic design automation and is currently working on high-speed I/O designs for the IBM Power Systems and IBM Z family of systems. And this, I will try to click playback and hopefully it will work.
Pasha, it seems like it's paused. Is it because
Sorry guys, seems like some technical issue with playback. Let me try again. Manju, can let me know if it's playing sound works now.
Good afternoon, everyone, or good morning, or good evening, depending on your time zone. My name is Chad Maquart. I am a hardware engineer at the IBM Systems and Technology Group, where I work to develop high-speed I/O interfaces for the IBM Z and IBM Power platforms. I'm here today to present the synchronous and low-latency die-to-die interface for the Z16 Telum processor, which I work to develop along with my colleagues, Mike Spear, Drew Turner, and Dan Drebs. So pictured on this slide is the Telum dual chip module that consists of two Telum Z16 processors that are simply just rotated 180 degrees with respect to each other. The synchronous interfaces that bridges them is highlighted in the center. So the east side of Telum processor A and the west side of Telum processor B. The goal of this interface is to bridge the two Telum processors so that two 550 millimeter squared chips effectively behave as one larger 1100 millimeter squared chip. So this provides the benefits and processing power of a much larger chip without being constrained to the reticle size of the technology and the corresponding, yield impact that you can hit from trying to build such a massive chip in the technology. The spacing of these two Telum processors is less than 0.5 millimeters, so this configuration really enables very short interconnects and very constrained interconnects in terms of minimum maximum length, where we're just talking a matter of several millimeters. So we're able to leverage this to develop this interface, and we're able to squeeze in over 1,388 data lanes operating up to 2.6 gigabits per second. Because we're able to achieve a synchronous interface, the chip-to-chip latency is 1 UI, which is half the processor speed of the Telum processor. The total power achieved here is only 1 watt, operating at 2.6 gigabit per second and at 0.9 volts. So we're achieving a power efficiency of 0.26 picojoules per bit and a total raw bandwidth of 3.75 terabits per second, or 468.5 gigabytes per second. These short interconnects really are leveraged to achieve this latency and this power efficiency. And the thing to note, that the packaging technology that was used here was chosen really just to meet the bandwidth requirements of the processor. But this is capable of being compatible with other package technologies, whether they're cheaper or more expensive, down to 40 microns C4 pitch. As I mentioned previously, keeping the latency of this interface down is a key part towards reaching our goal of having two chips in this DCM effectively behave like one larger chip. To accomplish this, the interface is designed from the ground up to be fully synchronous. So the dual chip module itself is synchronized by a single global clock network, which is illustrated with the simplified diagram on the left side of this slide. In this diagram, there is a Telum A, which is the primary chip, and a Telum B, which is the secondary chip in this example. If you follow the global clock network, you will see that the tank PLL from the primary chip gets forwarded from primary to secondary in a feed-forward path, and also is fed back upon itself as a feedback loop. Both this feed-forward and feedback are illustrated with the gray arrows in the diagram there. The reason for both these paths is the goal to keep clock latency matched across the DCM as much as possible. Additionally, there is a sense network that's installed into the global clock network that is intended to measure clock skew between the two chips. This is accomplished by forwarding the clock grid that is across each chip and doing a similar feed forward and feedback in both directions, from primary to secondary and secondary to primary. This is illustrated with the red arrows in the diagram. Again, the reason for the feed forward path and the feedback path in both directions is to keep the clock latency matched across the DCM as much as possible. The end goal is just minimize clock skew, especially with these circuits used to measure skew. It's important that we try to minimize error from mismatch of the paths as much as possible. Using this clock skew measurement network, static skew is capable of being corrected during initialization of the DCM. So with this skew correction, it helps compensate for differences that can occur in the DCM due to differences in process, voltage, and temperature. However, even with this static skew corrected out, dynamic skew that can occur over time due to noise, temperature fluctuations, aging, that dynamic skew is not currently capable of being corrected out with this design. Steps are taken in the design from the ground up to try to minimize delay sensitivity to effects like noise and temperature. However, there still is a significant amount of dynamic skew that can occur over time. That is going to introduce uncertainty in the arrival times of the clock grids between the two chips that must be factored into the margins used for timing this fully synchronous interface. With a common global clock network in place to synchronize both chips in the DCM, the data lanes of this DCM interface are now capable of being fully synchronous. A simplified diagram of one lane for this interface is illustrated on the left side of this slide. Following the path from Telum A to Telum B in this diagram, you'll see that it is indeed a synchronous latch-to-latch transfer without the need for FIFO because it is fully synchronous. And the bandwidth requirements of this particular project did not require the use of any SerDes. The latency of this interface is bounded really by the cycle times used to clock these synchronous latches across the DCM. Overall, reviewing this diagram, I think it's apparent that this is a very simple interface, especially when compared with other modern PHYs. The synchronous clocking, the short interconnects, we are very much able to leverage to trim out as much fat here and maximize on power and area efficiency with the design. Probably one of the biggest factors towards the power efficiency is the use of an open termination at the receiver. You know, without a low impedance termination there, constantly drawing DC power, the majority of the power is dynamic, so it will scale with voltage and frequency. Another thing that was done to keep the area and the power of the receiver down is providing a common power supply for both the driver and the receiver, which is designated by the VDDA section of the diagram below here. Notice that the VDDA supply from Telum A that's used to power the same digital logic as the rest of the chip is actually fed forward into the Telum B chip simply to provide power and level shifting to the signal being received. Once the signal has been amplified by the receiver, it does get level shifted to the local power supply of the Telum B chip, signified by VDDB. And from there on, everything downstream is powered by the same VDDB supply that all the rest of the digital logic is powered by. One more consideration with this interface that was added in order to ensure that there was adequate timing and margin across multiple conditions is the inclusion of replica latches. You can see from the diagram there's both a late and an early latch included, where the late mode latch has the data delayed by a programmable delay line, and the early mode margin latch has the clock delayed by a programmable delay line. Using these latches and comparing the outputs of them to the mission mode path, which is the capture latch on the Telum B chip, it's possible to monitor how much margin is actually available with this interface, both in the late or setup direction, as well as the early or the hold time direction. There are also delay lines in the path of the mission mode, but prior to getting captured by the receiver, which can be calibrated based on the amount of margin measured from the early mode and the late mode latches. And this is something we take advantage of to really optimize how much timing margin every chip has with this interface. The calibration routine performed on the path delay of the synchronous data lanes is described by the flowchart on the left side of this slide. Before this calibration is performed, a minimum required timing margin is programmed into both the early mode and late mode delay lines to ensure there is sufficient margin to guard against a worst-case clock skew and clock jitter event. During calibration, a pseudo-random bitstream or PRBS pattern is propagated across the interface where the values of the early mode and late mode latches are checked across each unit interval, or UI, in the pattern. The delay of the data path is incremented until the captured PRBS patterns are an identical match for both the early mode and late mode latches. Of course, if no delay line setting is found which satisfies both early mode and late mode margins simultaneously, then the calibration routine will exit with an error. However, for the operating conditions of the Telum DCM, this is only expected to occur in the event of a defect in the hardware, or if devices critical to the performance of the PHY are fabricated well out of spec. The figure on the right includes a timing diagram generated from simulations performed at worst case and perhaps somewhat pessimistic noise and operating conditions for the DCM interface. Stepping through the waveforms from the launching latch to the capture latch, this timing diagram illustrates the buildup of jitter that can accumulate on each voltage waveform over the course of multiple UIs. The largest contributors to this buildup of jitter on the data path are crosstalk noise, power supply noise, and offset inherent to the data path from various process conditions, local mismatch, etc. The delay calibration routines ensure there is adequate timing margin to guard against jitter present in the data path, in addition to clock jitter and dynamic clock skew, or overall clock uncertainty, that may occur over time while the interface is active. The sheer volume of data lanes included in the Telum DCM interface make it impractical to probe every signal C4 during test. A probeless test methodology was developed along with corresponding test circuitry to provide coverage of on-chip circuits and interconnects during wafer test. The diagrams on the left side of this slide shows how adjacent data lanes are daisy-chained together during wafer test to propagate test patterns across every lane of the PHY. This methodology also enables test coverage of signal C4 wires and DCM package interconnects after module assembly. Test patterns are propagated throughout the PHY at plane of record operating speeds. Early mode and late mode delay lines are programmed to validate that there is indeed adequate timing margins in place. The test patterns are also implemented to stress the interface during module test with crosstalk noise, simultaneous switching noise, and intersymbol interference. Spare lanes are allocated in the interface for yield recovery in the event that test identifies any bad lanes. For the Telum interface, an additional 2%, or 28 lanes, are allocated where software programmable muxes are used to execute a lane repair. Several of the key metrics of the Telum DCM interface are collected into a comparison table on this slide to compare with similar die-to-die interfaces. Key highlights I want to point out are the power efficiency at only 0.26 picojoules per bit and latency of only 1 UI. These two metrics are some of the best in class in comparison to other reported die-to-die interfaces. It's also worth highlighting the low overhead that this interface has in terms of spare lane usage and no need for forwarded bus clocks. Finally, this interface is very adaptable across numerous CMOS and package technologies. The simple architecture used for this interface can be implemented in just about any modern CMOS technology. The implementation of the individual drivers and receivers as both power and area efficient autonomous entities really enables scalability that is almost limitless. Some of the most significant constraints to scalability that should be considered when selecting a package technology are the C4 count, the C4 pitch, and the impact that the combination of those two have on the maximum interconnect length through the interface. So otherwise, I think that just about covers everything I was hoping to highlight today. I do want to acknowledge again the other authors who collaborated with me on this work, who were integral in pulling this all together. And that is again Mike Spear, Drew Turner, and Dan Dreps. Lastly, I also want to recognize everyone listed on this final slide who made a significant contribution towards the development of this interface. Without their hard work and determination, this interface would not have been possible, so thank you very much. Otherwise, for anyone watching this, thank you for your time.
Yeah, and Pavel, I'm available here for any questions, of course, if there are any after the
thank you,
presentation.
Chad. Yeah, thank you for the presentation and video recording. Yeah, quite amazing technology with especially the comparison between current state of the art and what you guys did, really impressive in terms of power and latency. Let's check if you have any pending questions on the Slack. And attendees, please, if you have any questions, don't hesitate to post on Slack. As for now, I don't see any pending questions.
Okay, well, yeah, definitely appreciate your time, and yeah, thank you very much.
Thank you very much, Chad. I will pause the recording.